This is session 20 for models in epidemiology and biostatistics. I'm Gordon Hilton Fick. For this session, we are going to consider three topics: odds ratio attenuation, which will take us back actually to the very first session in this collection of material. Then we're going to look at some data management matters. And then we'll finish this session with something called a slope ratio model. That's the plan. So to discuss the topic of odds ratio attenuation, we're going to go back to the simplest scenario that gives us these challenges. And that is the case where there are two 2x2 tables. And for this session, we're going to be looking at strictly population characteristics. We're going to have probabilities and fractions. First of all, the probabilities. We're going to suppose that there are two strata that we'll label just 0 and 1, and then we'll consider the outcome as either disease present or disease absent. As is standard, we will think of the disease characteristic as the rows and the exposure characteristic as the columns. And we will suppose that there are then four probabilities that for our purposes are essentially unknown. And we will see two fractions that are essentially unknown. In each case, the probabilities and the fractions we'll take to be any number, any possible value between 0 and 1. And we will be looking at some examples to aid us here. Just for example, let's suppose we are looking in strata 0, and we wish to discuss the probability of disease for those that are exposed. Then that probability, which is labeled P10 here, is the probability that a person in strata 0 that has exposure has the disease. And obviously then 1 minus that is those that did not. All right, so we have four probabilities. The probabilities for the outcome being present or the person having disease. These four probabilities. And we have 2 for strata 0, exposure yes and no, and 2 for strata 1, exposure yes and no. Now we're imagining then, what about a circumstance in which we possibly incorrectly did not stratify on the strata, and we're considering what our 2x2 table would look like if we did not stratify. In other words, we are thinking of essentially a crude 2x2 table. Then we need to understand in the population that we're attempting to study, we're going to have two fractions. We're going to have, first of all, a consideration of the individuals who do not have exposure. And this number, this fraction W sub 0, is then the fraction of individuals in strata 1 among those that were not exposed. So notice that this number and its complement refer to the individuals that were not exposed. And we're saying that W sub 0 then is the fraction of the population that are unexposed. That we are considering the population of individuals that are not exposed, and what fraction of those are in strata, or would be in strata 1, and then since we're in this very simple scenario, then the remaining 1 minus W sub 0 are those in strata 0. Then we can ask, among those who did have the exposure, what is the fraction that had that were in strata 1? So we're looking at the two groups of individuals in this hypothetical population. Those individuals who were not exposed and how they distribute between the two strata, and then for those who were exposed, how they distribute between the two strata. Now, you might be thinking, well, how do I reconcile that? Well, it could be, for example, let's just take an example where both of the weights are 1/2. That would be saying that in this hypothetical population, half of the unexposed are in strata 1 and half are in strata 0. Further, for those exposed, half are in strata 1 and half are in strata 0. Now, we know that in the real world, or this real, hypothetical population, we can ask, well, how would the individuals distribute between the two strata? And that distribution will depend on whether they're exposed or not. Okay. Now, again, just to keep in mind, we're thinking about a circumstance in which the weights could be any number between 0 and 1. Now, what we're going to be reconciling is the fact that when the weights are the same, we get certain phenomenon, and we'll discuss that in a minute. When the weights are different is when we get things that are, the challenging issue. Because we can then see that if we wish to think about the population characteristics here, we're going to have two risk differences, one for strata 0, one for strata 1, two risk ratios, one for strata 0, one for strata 1, and so on. Two odds ratios, two health ratios. Okay. These are terms that we've seen going right back again to session 1. Okay, now we can ask, what about these characteristics that we might think of as definitive? All right, we're thinking, if in fact we stratify on the two strata 0, strata 1, then these characteristics become definitive. In other words, there's no other issues involved. These probabilities then are taken to be, yes, the solid ones, the given ones. Now we could ask, what about if in fact we had just collapsed these two 2x2 tables into one? Well, we have then the challenges present. We have issues of modification and confounding. Now, the modification issue we're going to set aside for the time being and ask, what if there is no modification of a particular type? So, for example, if there is no risk difference modification, then we would be interested in whether or not the assumed common between the two strata is different from the crude. In other words, we're going to be asking about confounding, given that there is no modification of that type. And we could have then for each of the assumed case of no modification, we would then have two characteristics to explore. For example, if in fact there is no risk ratio modification, then the discussion is between whether the risk ratio assumed common is different from the crude risk ratio. And we have 4 of these. All right. Now, but what do we get And now let's take a look at the scenario when we assume that there's no risk difference modification. All right, let's take a look at that case first. Well, that means that the risk difference for strata 0 is the same as the risk difference for strata 1. Now, what is going to happen when we collapse the two 2x2 tables into one? Well, we get two probabilities. The first is the probability of disease for those who are not exposed. And it turns out that if we take the weights or the fractions here, in other words, this is for W0 is the proportion of this population among the unexposed that are in strata 1. Well, then that means that that particular element in the 2x2 table, then, the collapsed or crude 2x2 table, would look like this. We're thinking about now those fractions as becoming weights, as I just said a moment ago. In other words, we weight the two stratum-specific probabilities for those unexposed by the fraction of the population that among the unexposed that is in strata 1 and the proportion or the fraction of the population among the unexposed that is in strata 0. And we can do the same thing for the exposed, right? We can get these two numbers, the two stratum-specific probabilities for the exposed, weighted by the fraction of the individuals that are exposed that are in strata 1 and in strata 0. Now we can, in fact, use the fact that because of the fact, so we get these two numbers. These would be the hypothetical probabilities in the single or crude 2x2 table. And what we then find is that if we identify that there is an assumed common risk difference, then we get this expression relating the probability among the probability of disease among the exposed that can be expressed in this way, using the fact that the assumed common risk difference is given by these two expressions. All right. Now we get, just for a sense of grounding here, that then the crude risk difference would be the difference between this weighted sum and this weighted sum. That is the crude. And if we do the little bit of algebra here, we see that the crude risk difference is the assumed common risk difference plus the product of the difference between the two weights and the difference between the probabilities, that is in strata 1 minus strata 0 for those unexposed. There's many ways to express this. But notice that we get the very familiar scenario. If the weights are the same, if the weights or the fractions are the same, that means W1 is equal to W0, then the crude and the assumed common will be the same. Further, if the probabilities in the case of those unexposed are the same, then we get that the crude is the same as the assumed common. In other words, we get the prerequisite for confounding, and that is that the weights must be different and the probabilities among the unexposed must be different. And this can be expressed in multiple ways. So this is familiar. To have confounding, we must have that these two weights are different. And if they're the same, then there cannot be, with this with this nice formula here, we cannot have confounding. Okay. We've seen some of this before. This is kind of review, but maybe put into a slightly more technical context. Now what we're going to do is think more generally about the fact that, well, for each of the two exposure groups, we can think of those weighted probabilities and then consider that probability for the unexposed and the probability for the exposed as a function of the weight or the fraction, okay? And we can see again that if the two weights are the same, then we have that the probability, this probability for those in the this probability for the exposed and its relationship to the probability with the unexposed is precisely the assumed common risk difference. Notice here, though, that we're assuming that the weights are the same. In other words, we're thinking now about the vertical distance between that probability function for the exposed and the probability function for the unexposed. And that vertical distance is constant and is the assumed common risk difference. Here's a little visual to help that us orient. And again, such visuals we've seen way back in session number 1, but now we're looking at it specifically in the population context, where we're looking at probabilities and fractions, and we're not looking at estimates of these probabilities in this instance. Okay, so over here, when W is 0, we have then the two situations when we're in strata 0, and here we are with W equals 1. We're in strata 1. Okay, let's for example notice that we have then 0.4 minus 0.1. That is 0.4 here with strata equals 0 with strata 0. 0.4 and 0.1. There they are, 0.4 and 0.1. 4. That difference is 0.3. That is as we get from this choice of probabilities, the assumed common risk difference. Because if we were to look at, for example, strata number 1, we get that the two probabilities are now 0.9 and 0.6. There is the 0.9 here, right here, and there is the 0.6. And the difference again, the most crucial thing, this difference is again 0.3. Then we can notice that for any weight here, we can think of the two lines. The red line, that is the probability function for the exposed, and the blue line, the probability function for the unexposed, and we can see that those two lines must be parallel. Another way of seeing that is that for any particular weight, the vertical distance between the red and the blue will be 0.3, right? That is the risk difference, the assumed common risk difference. However, just briefly, if the weights are different, if in fact we take an extreme example here where the weight W0 is 0.9 and the weight W1 is 0.1, then we're saying if W0 is 0.9, we're saying that among the unexposed, there's a lot more people, a lot more people in strata 1. Whereas in the exposed, we see, that's back here, there's only 10% in strata 1. And so we get this point on the blue line, that is the unexposed, but with a very high weight, and this point on the red line for the exposed, but notice here that the weight is such that this distance between this point on the blue line and this point on the red line, that difference is now negative. In other words, the crude, if we had this circumstance where there was this difference in weights, the crude risk difference would be negative, even though the assumed common risk difference is positive. And this we would see very clearly as a circumstance where there's confounding. Now we can repeat all of the technical things I've gone through for the risk difference for the risk ratio. For example, if we then now assume that there's no risk ratio modification, then we get that these two risk ratios, the risk ratio in strata 0 is the same as the risk ratio in strata 1, and the assumed common risk ratio is this number, and it's also this number. Now, with a little bit of algebra, again, one can show that the assumed common risk ratio and the crude risk ratio now, where we're now going to use these two probabilities, this probability and this probability, with the collapsed or crude single 2x2 table, and putting in what the risk ratio is here, the assumed common risk ratio is here, we get this relationship between the crude risk ratio and the assumed common risk ratio. And you can see it involves this complicated looking object. However, it turns out again that this will equal that the crude risk ratio will equal the assumed common risk ratio again when the weights are the same or the probabilities among the unexposed are the same. Either of these being if this difference is 0 or this difference is 0, then the crude risk ratio will be the assumed common risk ratio. And we will also, and following through a little bit of algebra here, we get again that the log of the probability function for those exposed and the log of the probability function for those unexposed differ by precisely the log of the risk ratio of the assumed common risk ratio. In other words, these two curves will be parallel. Again, that would be the fact that that we have this parallelism is that we get the fact that confounding cannot be present if either the weights are the same or the probabilities among the unexposed are the same. And as a very brief example, we can see that if we choose some probabilities judiciously here so that we get an assumed common risk ratio of 4. Again, if you take a look at the case where we're in strata 0, we have this vertical distance, that is the log of 4, and we also take for strata 1 this vertical distance, which is again the log of 4. That means that these two curves, the red curve for the exposed and the blue curve for the unexposed, are parallel curves. And the vertical distance between the red and the blue is the assumed common risk ratio. Now again, it's when the weights are different that we have then, and the probabilities among the unexposed are different, that we get the potential for risk ratio modification. However, notice that if in fact the weights are the same, and we are thinking of a vertical distance here, there cannot be confounding, right? Because the vertical distance is the same, and we see that the two curves have the same vertical distance. Okay. Now we come to the new part of this particular discussion of two 2x2 tables. We know that if there's no risk difference modification, then we have that those two lines, one for the exposed and one for the unexposed, one for the exposed, one for the unexposed, are parallel. If there's no risk ratio modification, then those two curves, one for the log of the probability for those exposed and the log of the probability rate for the unexposed, right? The log of the risk ratio for the exposed and the log of the risk ratio for the unexposed differ by a fixed vertical distance. But for the case of the odds ratio, we get an unusual thing that happens. If in fact there is no odds ratio modification, okay, if the odds ratio in strata 0 is the same as the odds ratio in strata 1, we do not have this parallelism of the log of those two probability functions. It turns out that the vertical distance between the log odds function for those, the log odds for those exposed minus the log odds for those unexposed for a fixed given vertical distance, that is where the weights are the same for the two, that unfortunately that difference between those two log odds is not constant. This is what has come to be called by a variety of names, but perhaps the name attenuation is the best one to use here. Let's take a look. Let's take a look at an example. If we take a circumstance, and a dramatic one, perhaps you might be thinking, but it'll serve us here. That is that the log odds ratio in strata 0 is the same as the log odds ratio in strata 1. So here we're taking, for example, the case of strata 0, that is -8 minus -9. That's a difference of 1. So the log odds ratio in strata 0 is 1. And if we take -1 minus -2, we also get 1. So the log odds ratio in strata 1 is also 1. And the odds ratio then is 2.71, right, by taking the exponent. So here's what the visual looks like here. We have that here is the log odds rate. This difference between the two log odds, these two circumstances, is 1 for strata 1. And it's not quite as easy to see here, but here we have the difference is also 1. So here we're taking a difference between -1 and -2. And here we're taking a difference between -8 and -9. And when you look at these two curves, when you look at the red curve and the blue curve, you might be thinking, oh, well, looks like they're parallel. Okay, how about that? However, if we adopt a wise approach, and that is, let's now look at the difference between the red and the blue curve. In other words, the vertical distance between the red and the blue here. If we do so, we see the following. We see this difference. So notice that as we had insisted, the difference in strata 0 was 1. That is the log odds ratio in strata 0. Over here, we have the log odds ratio in strata 1. It is also 1. And previously, we would have had that for the risk difference and for the risk ratio, that for every weight in between, we would have had 1. But not here. In this particular case, the difference is a function of the weight. The weight that is assumed to be the same. In other words, the weight for the unexposed is the same as the weight for the exposed, or the fraction. The fraction for those unexposed is the same as the fraction for the exposed. Nevertheless, we have that the vertical distance is not constant. Now notice, if we assume that the weights or the fractions in the exposed and the unexposed and the exposed are the same, there cannot be confounding. That is a basic principle we have for the discussion of confounding. Nevertheless, we're seeing here that the crude odds ratio will not be the same as the assumed common odds ratio. My. Now, these are this particular issue has been known for some time, and it goes by a number of names. You will see in the literature that's referred to as non-collapsibility, even sometimes non-linearity. That one is, whoa, I really don't think that's a good idea. You will also see in the literature that sometimes this attenuation that we just saw, that is, that the difference between the red curve and the blue curve, the vertical distance between the red curve and the blue curve for the odds ratio situation is not constant and is less than what we would have had if for the case of the assumed common odds ratios. Oh, my. So, well, we don't want to blur attenuation with confounding. This is not confounding. Further, you will see, unfortunately, in some examples in the literature where the stratum-specific odds ratios are not the same. And so we have actually that we're blurring the issue with modification here. Now, again, there's been a lot written about this, but almost entirely with descriptions with 2x2 table examples, and sometimes even more elaborate examples. But our attention here is with the case where there's 2x2 tables. Okay, so what are we dealing with here? Well, we've got a dilemma, and that is that even if there is no modification of the odds ratio type and no confounding of the odds ratio type, nevertheless, the crude odds ratio will not be the same. It will be closer to the null, as it turns out, than the assumed common odds ratio. My. Perhaps the most important paper ever written about this particular matter was published by Dr. Myra Samuels. And this very important paper was published in Biometrica in 1981. Myra Samuels was actually one of the later students of the very famous Jerzy Neyman of the Neyman-Pearson research, and maybe so much to do with the theory of hypothesis testing. So Myra Samuels was a student of Jerzy Neyman's and did indeed complete a PhD under his supervision, and then took on a professional responsibility at Purdue University. It was during fairly early, actually, in her time at Purdue that she published this important paper on what we would now call attenuation. And remarkable work. Sadly, Dr. Samuels did not live long. She was only, my goodness, only 52 when she passed away in 1992. And needless to say, Dr. Samuels' work, very, very important and quite theoretical too. Some of this paper, I mean, there's the oftentimes quoted, it is easy to show that type of thing in that paper. Very, very tightly written, excellent publication. In any case, it was the earliest paper, to my knowledge, that demonstrated in a theoretical way that the crude odds ratio would always be closer to the null than the assumed common odds ratio. And there's many other results that she reports in this paper. Now, what is far from clear in Dr. Samuels' paper and in others that have been written, where the authors mainly are offering examples, is just how large can this attenuation be? How much closer to the null will the crude odds ratio be when compared with the assumed common odds ratio? Even when, just keeping in mind here, even when there's no confounding, when the weight for those exposed is the same as the weight for those unexposed, right? Well, what is certainly true, if you look carefully at this, is that if the health ratio is very close to 1, then the odds ratio will be nearly the same as the risk ratio, and we would anticipate that there would be very little difference between that then the attenuation issue would be very minor, because the odds ratio will be the same as, or almost the same as, the risk ratio. However, this is not well articulated as well, and as we'll see in a minute. Now, again, if we have comparatively small probabilities, and just as a very quick, if the probabilities are very small, then we can have that the health ratios will be nearly 1, and so the odds ratio will be nearly the same as the risk ratio. So a bit of technical stuff, not all that unfamiliar, frankly, and one that you can see in many of the illustrations that can be detailed here. However, we might then ask, well, what is that vertical distance as a function of the characteristics? In this case, the 4 probabilities that we have in play. That is the 4 real probabilities in those 2 by 2 tables. Okay. Well, it turns out that the vertical distance, that is, again, for specific cases of the crude odds ratio, but for the circumstance where the weights are the same in both the exposed and unexposed, it turns out that this vertical distance is made smallest for this particular value of the weight, or the fraction here. It's a bit technical, and I've written this in terms of something called the square root of h and b minus a, which are the probability. The b minus a is the probability of disease for those exposed, minus the probability of disease for those unexposed in strata 0. And then it turns out that this denominator here is the difference between the 2 risk differences. Oh my. Remember, we're assuming no odds ratio modification in this particular expression here. However, notice that, well, what happens if the there's no risk difference modification in addition to there being no odds ratio modification. Oh boy. Well, you would think, okay, this formula doesn't work because the denominator is 0. Okay. What happens in that instance? Well, there's more. It turns out that if there is, in addition to there being no odds ratio modification, if there's no risk difference modification, then the smallest vertical distance will always be when the two weights are equal to a half. My. And that can be shown with some fairly careful, a little bit elaborate, but some fairly careful attention to some math. Oh, we're skipping that. Now it turns out that there's a relationship between the probabilities in strata 0 and then implicitly in strata 1, that A and C, in the situation in which there is no odds ratio modification and no risk difference modification, we get that, well, it turns out that we can express A and C in terms of the assumed common odds ratio and the assumed common risk difference. Wow! So if there's no risk difference modification and no odds ratio modification, we get this interesting relationship between the probabilities for those in strata 0. And this interesting function, this plus or minus here, if for example C is greater than A, then C gets the plus sign version and A gets the minus sign version. Okay. And it does turn out that if there's no odds ratio modification, but the assumed common risk difference is small, then the vertical distance will be very small. Now, you can also determine that if, in fact, the risk difference is near the maximum attainable, and there's some math about that as well, then if the risk difference is large, in other words, near the maximum that's attainable with this setup, then there will be very, very minor odds ratio attenuation. However, when the risk difference is small, we can get a big difference between the assumed common odds ratio and the crude odds ratio, even though there's no confounding again, just to kind of hammer that home. Now, I just want to close this portion of this session by noting that all of what is presented here is in the population. We've got the 4 probabilities and the 2 fractions. And there's still quite a bit of interesting work that is underway with my colleague, Diego Nobrega. And some very, very interesting things are happening. There's quite a bit more to be done, as I said, and nevertheless, showing to what extent these results in the probability or the population domain look like in the case where there's actual variability, where there's actual estimates of the probabilities and so on, the actual probabilities of the actual fractions and so on, we get, still a whole lot of interesting things that need to be done. Now for the second portion of this session number 20, we're going to look at some issues in the design and entry and management of data. This is a topic that I'm often asked about, and there are a few, I think, important matters that I want to draw your attention to that I think will be of interest. This particular session has been included in many of my classes and other circumstances over the years. And the illustration that I'm going to use comes courtesy of Dr. Patrick Hessel, who was a professor in of epidemiology at the University of Alberta. And he very kindly offered this questionnaire and a portion of the data from this large project that was conducted, my goodness, quite a number of years ago now, back in the mid-1990s. But it serves to illustrate many issues. And I wanted to point out here that, in fact, the primary research question, there were a number of research questions, but the primary research question was looking at the relationship between asthma in children and limitations to their play or their daily living. And this questionnaire asked a number of issues, but the crucial ones that, for our purposes here, we'll focus on had to do with this association between asthma in children and limitations to their play and their daily living. So what we had for their purposes here was the need to construct definitions of exposure and disease. In this case, the disease is the limitations to play, and the exposure here is whether or not the child had asthma. And then we can address many of the challenges that might come up and how to explore the study of this issue. So here is, very briefly then, the questionnaire that was used back in the day. And I noticed that it was just referred to as a school health survey. It did not specifically detail what their primary research question was. The idea being here that we did not want to in any way kind of influence how the parent might answer these questions by giving them cues as to what the study was about, really. Now, this kind of anonymizing of things is always a good idea. The next thing that I'd like to point out to you is that if it's at all possible with primary data collection, and the age issue is important, ask for the person's date of birth, not their age. Ask them for their date of birth. Then their actual age in days can be computed from their date of birth and the date in which the questionnaire was obtained. One of the commonest challenges that I have seen over the years is circumstances in which age was merely given as a number, not even a decimal, and in fact, people sometimes are very, very weak on actually, well, are you close to your birthday or what is your age? But everybody knows their birthday. Okay. Now, I'll also notice here that everything here was coded. So the gender of the child and the results of each of the questions. We'll see, it turns out that even the student's school was coded and the town was coded. Everything had numerical codes attached to the responses. Okay. And you can see that there was quite a bit asked. They asked about their limitations to their activities, and they asked a quite open-ended set of things about what conditions limit your child's activities. Okay. So there was quite a bit of data being collected. Here, these numbers, these responses here had to be coded before they were entered. And I'll comment a bit more about that in a minute. Okay, so notice the codes are here. for a lot of this instrument, of this questionnaire, and other things needed to be coded before data entry was completed. And some of the questions were conditional, and I think I will let you have a look at this instrument. It's certainly available in the slides. And it is a very good example of a well-designed questionnaire, in my opinion. My goodness, from October of 1994. Wow, quite a bit of data that was recorded here. So inevitably then, we have then the actual distribution of these questionnaires, and then the collection of the data that was the actual, if you like, actual raw data. Then the challenge is data entry. One of the issues that one faces almost right away is, should the data be entered into a spreadsheet or a database or a word processor or a text processor or directly into statistical software? These are challenging issues. Most of the time, I would suggest that there are arguments for the use of any of these methods except the word processor, where there can be issues with the importing of the data from a word processor. And notice I'm distinguishing the word processor here from the text processor. Word processor is a fairly general term. Entering the data directly into statistical software has some merits too. Entering it directly into Stata or directly into R, for example, are options. Entering it into a spreadsheet program like in OpenOffice or a database system like in OpenOffice. The spreadsheet in OpenOffice is called Calc. The database in OpenOffice is just called Base. And the word processor is called Writer. But again, I would argue that it may be better not to enter the data into a word processor. And you can all, I'm sure, come up with the Microsoft Office version of these things. Now, one of the things that is important is if this data is to be collected for statistical analysis, it is almost always a bad idea to enter the text parts directly. In other words, the actual responses. It's better to have things coded first. And then you can later on, if you wish, in the building of a coding manual, which can be pretty substantial, you can then enter the codes into your database or your spreadsheet or your whatever tool you're using, and then use your analysis system like Stata or R to display labels for the codes. And again, I'll show you an example in a minute. So it is better to code it first, and then when you're creating the primary data set, to then enter the codes, and then as a part of a script that you use to set up the data for analysis, you can then have the labels appear, and the labels then being the text essentially that's needed. One other point that often comes up with students who are fighting with data management matters is the importance of keeping straight whether you have a PDF file or a writer file or a text file or a spreadsheet file and so on. And if your computer system is using settings that hide this extension, this suffix or extension to to a file, it can be very confusing. And so I highly recommend that you find the way to ensure that you do see these extensions. It's something that pops up all the time for people when they're faced with primary data collection and then are dealing with files with different extensions, and meaning they have different types, and so they need to be able to conduct this. So here are the OpenOffice. This is OpenOffice text, OpenOffice presentation, and so on. So in Windows and in Mac and in Linux, how you get to see the extensions varies from operating system to operating system. You're going to look for something like in the identification of the properties of how files are displayed for you, something like an option like hide file extensions for known file types. You want that unchecked so that it is not hidden. Again, with some operating systems and some people's computers, this hide file is checked by default, and you need to uncheck it. Okay. So let's go back to the data again. All of the data was coded here. They had data from 4 communities and quite a number of schools throughout these Alberta communities. And it was a long and very, very complex data management, data entry, data design process for this project. So we had then in this instance that the exposure was that the child has asthma, and the absence of exposure was no asthma. And here the disease status was for the purposes, it was the limitations to play. Now you could say that's not really a disease, but we'll argue that. They had lots of things to look at here. And I'm only going to give you something very brief things. All right, let's have a look at some of these characteristics. Many of you will be familiar with the notion of a spreadsheet as distinct from a database. Databases are not flat or need not be flat, whereas a spreadsheet is a rectangular array, whereas a database can be vastly more complex. But if it's appropriate for your project, having a single rectangular array, often called a flat file, can be a good option. Now, again, the use of a single flat file or a single rectangular array of data is not necessarily required by systems like R anymore. And there are ways of having multiple files within R. And that's, again, a quite different topic. So for this project, there were quite a number of children that were included and quite a number of characteristics that were measured for each child. And here's what the, if I may, the spreadsheet might look like. I'm showing this using OpenOffice Calc. And you can see that if I'm able to import the data, which is in a comma delimited version here of a text file, okay, then OpenOffice is happy and immediately can accept this data for view. So notice here we have a rectangular array. We have the subject identifiers here as the rows. The subject themselves, ID, is a column. So we have rows and columns. In this case, a fairly big one. Notice here that everything's coded. Okay? We have their date of birth. We have their grade in school, the code for the school they went to, the code for the town, and so on. Everything was coded. Now, many people these days might be in a position where they want to set up their data in a database, and there are certainly a number of good reasons for that. The crucial thing will be understanding the differences between the database system you're using and the spreadsheet system you're using. There can be built-in differences between database usage and spreadsheet usage, and these can be important. Okay. Now, one of the things that comes up quite a lot is that if you decide, if in fact you're considering about whether or not to use a database, some well-designed databases, including Base in OpenOffice, enable you to create a data entry form directly from the database that you are establishing, and that can be very helpful. Okay. So there's many issues here relating to a database compared with a spreadsheet. And in fact, I think I'm not going to focus on that, but there are issues that are in play that are important. They're very much like constructing data frames in R and or databases with multiple flat files that have linkages. Many issues for you to explore. And as I said, the data entry forms that you can create from a database system can be the sorts of things that people can use directly on their computers or perhaps printed off. So there's various options here. Should the data entry forms be all entirely handled online? There's some advocates for that now. And there's still some that would suggest that, well, maybe it's better to have the standard backup, if I may, of your data entry being collected in hard copy and then entered afterwards. So data entry, and sometimes it's still important to, scrutinize how the data entry process will work. Will there be data entry errors? Data entry errors can occur perhaps more often if you're then taking the hard copy printed data forms and then entering them into a software system on a computer. But there can be issues with data entry problems if people are being asked to use an online data entry system. This is a changing dynamic, in my opinion, and isn't necessarily definitive one way or the other. But I think it's increasingly people are becoming more and more comfortable with completing data online. But again, this is not a done deal all the time, depending on the circumstances. So there's other issues here related to data entry. If you are going to have your data, should you be using something called a fixed field format? This is somewhat dated, but it's still widely seen. And Stata and R do both still accept data that is entered into the software using fixed fields. You can read about that. More commonly, perhaps, are where you have a delimiter in the file, which determines the where a field starts and ends, based on the simplest being just having a space between the fields. However, spaces alone can be sometimes a poor choice if the actual fields can contain spaces. Comma delimiters are widely seen, but again, if embedded commas can appear in a particular field, this could be a problem. Same thing with many of these instances. Again, we're thinking about a text editor format and the choice of the delimiter. So, for example, this is how this data for this asthma study looks like in its raw form. In other words, as a text file with comma delimiters, okay? So you can see that it's sort of unreadable in a way. It's how we look at it, how we see it is not friendly. However, importing data with comma delimiters like this into either a spreadsheet program or a software system like Stata or R is absolutely straightforward. This is not a complicated issue. Again, so long as your actual data doesn't contain any commas inside a field, then you can get into trouble. It's important to keep track of here, by the way, if everything ends up correct, that the number of children is correct, that the number of fields for each child is correct. Many tough issues here. So as I said a little while back, should you use a word processor for your data? Probably not. These days, many people have commented over the years with projects I've been involved in that what you want is the ease of transfer of your data from whatever file system you've set up and whatever system you've used into your analysis system, which could be R, could be Stata, or perhaps could be data that's being entered into Python or Julia or other programs, other statistical analysis systems too. Okay, so keep in mind that it is almost always not a good idea to use the default of if you import your data into a word processor, saving it as a document file, not a text file, can get you into trouble because it may not be easily importable into the analysis system, which is the crucial thing. Your gold standard file should not be a file that has a word processor suffix, okay? Not .odt, not .docx, docx, and so on. So many people have faced this over the years when you inherit data for your project. Many students are not doing primary data collection, but are being given data that may have been collected for another project, or maybe they are a part of the project, but it was underway perhaps before they even came on board. So they're inheriting an existing format. What you want to have, though, is the ability to establish a gold standard file, then have mechanisms in play to create the file for analysis, but you want to keep track of what you've done to that gold standard file when you've, say, imported it into a statistical analysis system that you can easily repeat. Again, this is a challenging issue. Students and researchers often face the fact that they might receive an initial file that might be thought to be maybe complete. However, it can often be the case that the people who are the managers of this primary or gold standard file may update it. They may change it. You're going to have to keep track of that. You're going to have to be the one that has the ability to take a new file from the person that was handling data management for you and process it in a way. And I'll show you an example in a minute. Other things that are crucial to keep track of when one is inheriting or becoming a part of a project that's well underway is being clear about the variable definitions. And I'll just give you one quick example that might come up. You may have a field that has a name. It may be smokema. And you may think, okay, that's referring to the smoking of the mother. But more crucially, is that field their current maternal smoking status, or is it that the mother has ever smoked? In other words, you need to have in the coding manual and in basically the documentation for the data that you are inheriting, clear definitions of what these variables mean. Because as anyone in epidemiology and biostatistics will tell you, knowing the current smoking status of a person is quite a different thing from knowing whether or not that person has ever smoked. That's just one example for you. Okay. Here's an example of a script that one can use to take a file, a gold standard file, importing it into a system like Stata, and then carrying out some processing. Here is essentially a portion of what would have been good to know with the codes that were crucial for and what we want to see in our report, in our output from the analysis system, is the labels for the codes and not the codes. The codes you don't want to have to keep track of, right? You want to be able to be able to look at the results from your analysis system with friendly labels. Here, by the way, is how Stata would take the date of birth and the date in which the survey was completed, and enabling you to compute a numerical value for their age. So this function in Stata, MDY, enables you to compute the number of days between the date in which the survey was completed and the person's date of birth. And the idea then is that you actually know their age, and you know it in days, not in or in years, but in fractions of a year too. You can see that this numerator of this expression is the days, and then we divide. Again, it's somewhat approximate, but by 365 and a quarter to get the year. All right. Notice other codes attached with variables can be built, and you do so in a file that you keep. In Stata, it's a do file. Okay. You have scripts that keep track of the decisions you've made, so that the variables that you have that have labels, and the labels make sense to you. Here's also an example of a script that's doing some data cleaning. Here, for example, we're seeing that this variable kind play should be interpreted for the analysis as a missing value if the entered code was either an 8 or a 9. Now, it brings up another issue. Should you use a missing value code in your gold standard file? Many would argue that that's not a good idea, that you use a numerical value for missing, like a 9 or a 99 or something, instead of, in Stata, a dot, or in R, an NA, because then you're tying your gold standard analysis to the software system. Not a good idea sometimes, okay? So again, the choice of the codes you use can often be considerable advantage to this sort of thing. In other words, using numerical codes for missingness and then recoding them as missing in the system that you're using. In R, it's the missing value code is not dot. It is capital NA, and there are other parts to it in R as well. Okay. So after, just for illustration here, showing you what the data editor would look like in its browser form, after the codes have been assigned the labels using those two scripts that I just showed you. The script that mainly was about constructing the labels for the codes and the assignment of missing values to the missing value codes in the original file. So you can see that Stata is very happy to now report what looks like text, but it is not. This data is still codes with labels for the codes, which enables vastly more forms of analysis in Stata and R to have numerical values rather than text values. Okay? So keep straight here that these blue cells here are not texts. They are actually that Stata is showing you the labels for the codes. So here, just very quickly to wrap up the second part of this session, is using Stata after we have correctly run the scripts to label the variables correctly and to use the correct missing value codes, we get what might be the start to an important analysis. That is the relationship between asthma and limitations to the amount of play. And you can see here that we get, at least for the moment, a quite striking difference that a child has limitations to the amount of their play, just slightly more than, roughly 2% of the time in this data if the child does not have asthma. But if they do have asthma, it seems that they have limitations to the amount of play 33% of the time. So this big difference between the two might be of interest to this project. Okay. So we get this big risk difference between the two, as we've looked at earlier. And there's, of course, way more analysis that could have been done with this particular study. But this is just to show you how we have the data entry form, we distribute it to the collection of individuals we wish to have in our study. We then code the responses that the participants give us. This is in this case the parents. And then we imported this for this illustration, the data into Stata here. And so that is the second part of this session on, again, really just a taste of some of the issues that investigators face with data integrity, data analysis, data design, data management. It did turn out, by the way, that there was quite a bit of data cleaning needed. If you use some of the basic tools for assessing data integrity, many of them coming from, for example, the work of John Tukey in exploratory data analysis, we get odd things in this data, like, for example, a 10-year-old child in grade 1, and things like that need to be checked, that would have, way back in the day, again, we're talking about a very old project now, but back in the day, was that child actually in grade 1? Was their age correct? Again, data integrity being an important issue. All right, well, now I'd like to take just a few minutes more for this session to talk about one large class of models that we have not seen before. Maybe I refer to it somewhat vaguely and indirectly, but there's a large class of models called slope ratio models. Oftentimes they're seen, widely seen actually, in studies of biological assay, but their usage is very widely seen and widely used. I have, as an example for you, a data set that was from a paper of David Finney's from 1951. It's an old data set. And I highly recommend Finney's textbook on statistical method in biological assay. There are many others that are worth exploring here. This section of this session will only be a taste. So what is it about slope ratio models? Well, it turns out that the objective here was the construction of a model that gives us curves that emanate from a particular point. For illustration here, to get us started, let's think of the model that I'm showing you here. This is where we are going to have an expected response. We've got two characteristics. We've then got the different doses that this preparation will have in two forms, a standard form and in a test form. And we're wondering about the relationship between the standard form and the test form. And now we're going to get a little more specific here. And that is, if in fact we use a model that gives us two lines emanating from dose of 0, in this case, a 0 dose of a test preparation should have the same response as a 0 dose of the standard preparation, right? So it turns out then that the model should look like this if we wish to have two lines emanating from a particular value when the dose is 0. So we're going to have T will be 1 for those receiving the test preparation, and T equals 0 for those receiving the standard preparation, okay? Then we can see that this line, if you specialize it, and we've done quite a bit of this, we specialize it to T equals 0, that's for those receiving the standard preparation. We get this line with this intercept at D equals 0, and this slope. And for the test preparation, we get the same intercept when D is 0 and a possibly different slope. So notice here that B2 is the difference between the slopes. But B0 is here the assumed common intercept. In other words, this model is going to give us two lines of different slopes, but emanating from the same place when the dosage is 0. Now, there's quite a bit of literature on whether or not one is in a place to assume that data at various dosages will retain this linearity issue for possibly very small doses, and indeed for the 0 dose. So that this assumption that the two lines emanate from the same point deserves attention that's related to the assumption of linearity here. Now, we come to the second new issue for you here, and that is that we are going to be able to discuss something called the relative potency. And here we'll just use the symbol K for that. K here, a population characteristic that suggests that the D doses of a test preparation give the same expected response as KD doses of the standard preparation. So for example, if K is greater than 1, that's saying the test preparation is more potent than the standard preparation. And if K is less than 1, it's saying the test preparation is less potent. There's a relationship between the regression coefficients that we would get from our model and this crucial issue, that is the relative potency here. Okay, so here I'll show you the data in a minute, but here is the regression analysis where we have the response, which is assumed to be a measured or continuous response. And we have two explanatory variables. We have D and TD. Now, I will point out to you here, notice that the variable T is not included here. You would say, wait a minute, if we're going to include, for example, the interaction of T and D, shouldn't I have both D and T in the model? This has to do with the issue of centering. In other words, should we be in a position to assume that if we center the variable D, which is dose, about some value, that the regression coefficients we get would be invariant to that centering. The crucial regression coefficients would be invariant to that centering. That is the so-called, hierarchically well-formulated assumption that you see in some literature. Well, the slope ratio models that we're looking at here do not have the centering option. We would not center dose because the dose of 0 here is crucial. It is central to this particular circumstance. It is changing or centering dose changes everything. And that's correct because something specific about this model and the fact that the two lines must emanate from a 0 dose is crucial to the use of these models. Okay. Now I'll also point out for you here that once we have carried out this regression analysis, and we've used in Stata the regress command, that we then can consider the estimation of the relative potency. Okay? And in Stata, that's nicely available to us. It's nicely set up for us. Turns out that we can indeed use a command in Stata called nlcom. That is a post-estimation command that we're using then the regression coefficients, estimates that come from the fit, to construct an estimate and and some confidence limits for the relative potency here. And this is something we haven't seen before. This method that the NLCOM use is called the delta method. And those of you in the biostatistics world might want to look up delta method and see exactly how that works in this particular context. There is, by the way, another method widely called the Filer method that is typically very close to the delta method. But again, this is slightly taking us off topic here. And I didn't want to go too many miles away, except that those of you who are interested may want to refer to the very fine work of Daniel B. Delury. I think I may have made note of this. If you go to my website, which is available to you, I've included the works of Daniel B. Delury, his regression notes, his experimental design notes, and his introductory course notes on my website. So you can find out more about Filer, or you can look up the Filer method elsewhere. Okay, I'm kind of meandering a tiny bit off topic here, but to point out that in this case, we get an estimate of the relative potency of 0.6847, and we can see then that the test is not as potent as the standard in this particular project. The confidence limits certainly nowhere near 1. Okay, even the upper limit of the confidence interval here we can see is not near 1. So we have, again, a test of significance here of the relative potency that's available. The point being here, this is actually a test of significance for k being 0. That's not really what we're interested in here. The point being here that it's not 1, okay, or it's certainly not greater than 1. Okay, I'm a little, okay, that's just a quick example for you of that. And a reminder that this model, we would not center the dose variable because the 0 dose is special here. And so such models, such slope ratio models, are not hierarchically well formulated. Okay. And again, there's some literature, there's some textbooks in which they argue that all models should be hierarchically well formulated. And well, that is a good principle, but you need to assess why things should be hierarchically well formulated. And the centering issue is really at the heart of this. Okay. So here's what the data looks like here. We get two fitted lines coming from the 0 dose. We get the standard, which is this green line, and the data for the standard, and the orange line is the test. Okay, and you can see that we have we have the 0 dose, and we had a single dose and a double dose in this small illustration here. Nevertheless, you will see that there is a further thing I want to spend just a little more time with you on, and that is the assessment of whether or not we should be assuming that it is okay to assume that these two hypothetical or population lines emanate from the same point at the 0 dose. And in data, we can reproduce what is given in David Finney's article, and I'm including it here for you. There are 2 tests of significance associated with whether or not we should be assuming that these two lines emanate from a point. And I'm going to refer you to Finney, either his papers or his books or other places. You can see that both of these tests of significance have very high p-values, and there's no evidence against the assumption of validity. Here is the issue. Validity of this assay, or validity of the model that is assuming that the two lines emanate from a point. It turns out that the methodology given in Finney, which is a little bit complicated, is essentially, well, it is the same as repeating this work with the consideration of a nonlinear model with two parabola, for example, that are emanating from that point at the zero dose. If you can look again, this is another example of a model that's not hierarchically well formulated. The two parabola are obliged to come from the same point at the zero dose, the zero value in both cases. And you would say, well, we don't have the variable here, t, right? It's missing. However, it's missing on purpose, missing for a reason. In any case, if you do this parabolic approach, which perhaps is a little more intuitive than that given in Finney, but again, there's merit to seeing all the thinking involved here. And it does turn out that you get essentially the same results. The regression analysis gives us these tests concerning nonlinearity, and these amount to the validity tests, because the two tests of significance that we get that involve the nonlinearity are identical to the two tests that are given by. So the nonlinearity tests are the same as the tests given by the validity tests that are shown in Finney and in various other places. And I do have in this file slope ratio, other examples for you, but I think that I'm going to close off this session number 20 now. If you are interested in exploring the possibility of slope ratio models and the whole large topic of models that are not hierarchically well formulated, and the rationale for them that can be very crucial and can be very important in some statistics and some epidemiology.